Every single day, millions of people, they sit down at their computers, open up a chat window, and just type in a prompt.
Yeah.
You hit enter, and within milliseconds, a cursor blinks, and words just start appearing on the screen. It really feels like you are talking to an entity, like a mind.
Right. I mean, it's designed to feel that way.
Yeah.
But obviously there's no physical brain there.
Exactly. If you open up the server rack, you don't find a mechanical gear you can turn or a fuel line you can trace, right? There's no visible engine that you can understand just by looking at it.
No, it is entirely intangible to the human eye. We are dealing with an architecture that, well, it exists purely as a landscape of mathematics.
Suspended across thousands of silicon chips.
Exactly. Suspended across thousands of chips. And for almost everyone who interacts with it, it is the ultimate black box. You see the input, you see the output, and that vast trillion-parameter ocean in between is just treated as magic.
Well, welcome to the deep dive. Because today, we are taking a crowbar to that black box.
We really are.
We are opening up the architecture of the most powerful artificial intelligence systems on the planet, specifically the transformer.
Yeah, the core engine of everything right now.
Right. We are going to look at the exact mechanical, mathematical, and structural gears turning inside them. We want to break down how they process information, how they coordinate across massive supercomputers without just melting down.
Which is a real risk.
Yeah, and the deeply elegant mathematical tricks that allow them to synthesize human thought.
And our sources for this exploration today come from a highly technical, really granular dialogue that dissects transformer mechanics.
It's intense stuff.
Very.
Yeah.
It covers the extreme engineering trade-offs required to train these models, the evolution of how neural networks process layers of data, and the precise math that actually gives words their meaning and context.
So the mission here is to take concepts that typically live behind the walls of computer science PhD programs.
Right.
Things with intimidating names, right? Like distributed tensor parallelism, the residual stream, and rotary position embeddings.
Very scary sounding terms.
Exactly. And we want to translate them. We want to strip away the jargon and show you the underlying logic. Because by the end of this conversation, the goal is that when you see an AI generate a sentence, you won't see magic anymore.
You'll see the geometry.
You'll see the geometry and the engineering that made it happen.
And that transition, from seeing it as magic to seeing it as a masterpiece of human engineering is profound.
It really is.
Because the reality of how these models are built is actually far more fascinating than the illusion of a ghost in the machine.
I completely agree. So to even begin talking about how a model like GPT-4 or Llama thinks, we first have to talk about how it physically survives being created.
Yeah, the survival part is key.
Because these models are so massive, they just can't fit on a single computer. They are trained across clusters of thousands of graphics processing units, or GPUs.
Thousands of them working in tandem.
Right. And apparently, keeping all those chips coordinated is an absolute nightmare. In fact, there was a detail in the source material that made me laugh. Someone on a forum was asking a highly technical question about a parallel pair.
Oh, right, the parallel pair.
Yeah, exactly. The kind of typo that reveals a massive piece of the puzzle. They meant to type parallel layers.
Right, which is a huge concept.
And understanding parallel layers requires us to first look at the massive physical bottleneck that forces AI engineers to, basically compromise on their own mathematical designs.
It's a compromise. That's exactly the right word for it.
Let's visualize the original design first. Like the classic standard way a transformer processes data. It's called a serial architecture, right?
Correct. The sequential flow.
So from what I gather, data enters a transformer block, and it goes through a very strict sequence. First, it hits the attention mechanism. That's the part that looks at the whole sentence to figure out context.
Exactly. It finds the relationships between the words.
Right. The attention mechanism does its math, it updates the data, and then it hands that newly updated data over to the feed-forward network, or the MLP.
Which acts like the model's internal memory.
Or its encyclopedia. So step 1 finishes, then step 2 begins.
That is the sequential flow, yes. The data state is modified by attention, and that newly modified state becomes the explicit input for the MLP.
So the MLP relies on attention to have already done the heavy lifting.
Precisely. It needs the attention layer to figure out what words in the sentence are relevant to each other first.
But the sources say that in newer models like PaLM or GPT-J, they employ this parallel layers hack. They just change the rules.
They do.
Instead of sequential, The attention mechanism and the MLP are placed side by side. They both look at the exact same incoming data at the exact same time.
Simultaneously.
Right. They do their calculations completely independently, and then their final answers are just added together at the very end of the block.
That's the hack. Wait, hold on, though. If they run at the exact same time, the MLP is totally blind to what the attention just did. It is.
If the MLP is supposed to synthesize information based on the context that attention finds, aren't you functionally crippling the model's reading comprehension by hiding that context from it until it's too late?
That is a highly astute objection. You are identifying a real mathematical degradation in the model's logic.
So it does make it dumber.
By running them simultaneously, yes. The MLP cannot benefit from the immediate, localized context that the attention layer just extracted.
It's stuck using the old data.
Exactly. It is forced to make its calculations based on the older, less refined data state. So, strictly speaking, you're losing a degree of expressive depth in that specific block.
So why do it? I mean, why intentionally make the AI worse at reading?
Because of the physical realities of the hardware.
The cables and chips.
Yes. When you are operating at the scale of hundreds of billions of parameters, that tiny mathematical loss in logic is swallowed up by the sheer vastness of the network.
So it's so big it just doesn't matter.
The model is so large, it simply routes around the inefficiency. But the reward you get on the hardware side, the sheer speed, is what makes training these titans possible in the first place.
Wow.
The entire hack is designed to minimize a horrific communication bottleneck called all-reduce.
Okay, I want to spend some time on this because understanding the hardware constraints completely reframes how you look at the software. How does all-reduce work?
We have to step back and look at how a giant matrix of numbers is processed. A single weight matrix in a modern large language model is far too massive to fit into the memory of a single GPU.
Right. They're enormous.
So engineers use something called tensor parallelism. They take that giant matrix, chop it up into smaller fractions, and give one fraction to GPU number 0, another fraction to GPU number 1, and so on.
So thousands of GPUs are all working on tiny puzzle pieces of the exact same math problem.
Yes. They run their calculations on their specific puzzle piece. But eventually, to get the final answer for that layer of the neural network, they have to put the puzzle back together.
They have to sync up.
Right. They sync up over the network cables connecting the servers, share their results, and mathematically combine them. So every single GPU has the complete updated picture before they can move on to the next layer.
And that synchronization protocol is the all-reduce operation.
Exactly. That is all reduced.
The sources use a really grounding analogy for this. Imagine 4 friends going on a road trip. They represent GPU 0, 1, 2, and 3.
Very expensive road trip.
Yeah, very. So over the course of the trip, they all pay for different things. Gas, food, hotels, and they each keep their own receipts.
Okay.
So GPU 0 knows it spent $10, GPU 1 spent 20, GPU 2 spent 30, and GPU 3 spent 40.
Yeah.
Now the trip is over.
And it's time to settle up.
Right. For anyone to know how much they owe or are owed, every single person in the car needs to know the exact total amount spent on the entire trip.
That perfectly illustrates the 2 phases of the operation. First is the reduce phase.
Reduce meaning addition, right?
In this context, yes. Reducing means applying a mathematical operation across all the data. In this case, addition. The system sums the values. 10 plus 20 plus 30 plus 40 equals 100.
Okay, so that's the total.
And the second phase is the broadcast, or all phase. That total of 100 must now be copied and transmitted back into the local memory of GPU 0, 1, 2, and 3.
So they all get the final receipt.
By the end of the operation, every single chip holds the identical number, 100.
But the problem isn't the addition, right? I mean, GPUs can do addition in a nanosecond. The problem is talking to each other.
Network bandwidth is the absolute bane of distributed computing. Transferring gigabytes of data back and forth across physical cables, even incredibly fast ones, creates massive latency.
They just have to wait.
Exactly. The GPUs finish their math instantly, and then they sit there idle, doing absolutely nothing, waiting for the network to finish passing the data around.
And this brings us right back to why the parallel hack is so brilliant. Let's look at the old serial way. The data hits attention. The GPUs do their fragmented math. Then they have to hit the brakes and do an all-reduce sync across the network to put the attention puzzle together.
That's one sync.
Right. Then they take that synced data, feed it to the MLP, do the fragmented math again, hit the brakes again, and do a second all-reduce sync to put the MLP puzzle together.
That is 2 massive traffic jams for every single layer of the model.
But with the parallel architecture, If attention and MLP are completely independent and reading from the exact same starting data, you can mathematically fuse their fragmented operations together.
You combine the work.
Yeah. You let the GPUs calculate their piece of the attention math and their piece of the MLP math all at once. They generate one combined puzzle piece.
And then
Then you only have to do the all-reduce synchronization once at the very end. You cut the network delay exactly in half.
you do. In the physical reality of supercomputing clusters, having those communication operations yields roughly a 15% boost in total training throughput.
15% is huge.
When training costs tens of millions of dollars and takes months, a 15% speedup is an astronomical saving. They deliberately chose to make the math slightly less elegant to appease the physical limitations of the network cables.
Wow. But even if you only have to sync once per layer, doing an all-reduce with a cluster of thousands of GPUs sounds impossible.
It is incredibly difficult.
Going back to the road trip, if everyone tries to hand the receipt to the driver to do the math and chef the answer back, the driver is going to be completely overwhelmed.
Right, the central node fails.
Yeah, if 4,000 GPUs try to send gigabytes of data to one master GPU at the exact same microsecond, that master GPU's network card would literally melt. It would instantly crash the bandwidth.
This is a classic topology problem. A master-worker architecture, or a star topology, fails at scale because the center node becomes an insurmountable bottleneck.
So how do they fix it?
This is why AI training relies on an algorithm called ring-all-reduce.
Ring-all-reduce. So they eliminate the master GPU entirely and put them in a logical circle.
Picture those four friends sitting in a circle. Instead of handing their receipts to a central person, they slice their receipts into chunks and pass them to the person on their right.
Okay, so it's a circle of passing.
The algorithm works in two distinct phases. Scatter-reduce, followed by all-gather.
Break that down for me.
Let's slow down. Imagine the final data array we need to build is divided into four chunks: A, B, C, and D.
Got it.
In the first step, GPU 0 sends its piece of chunk A to GPU 1. At the exact same time, GPU 1 sends its piece of chunk B to GPU 2.
And GPU 2 sends C to 3, and 3 sends D back to 0.
Exactly.
So nobody is sitting around waiting. Every single GPU is simultaneously uploading one chunk and downloading a different chunk.
The network is completely saturated.
But the load is perfectly distributed. Nobody's getting crushed by receiving everything at once.
They continue passing and adding these chunks around the ring. By the end of the scatter-reduce phase, the total sum has been calculated, but it's distributed.
What do you mean distributed?
GPU 0 holds the complete global total for chunk A. GPU 1 holds the total for chunk B, and so on.
I see. But they still don't have the full picture. They only have their specific completed slice.
Which triggers the second phase altogether. They do the exact same ring passing motion again, but this time they aren't doing any math.
They're just sharing.
Exactly. They're just copying and sharing their completed chunks until every GPU has a full copy of A, B, C, and D.
That's brilliant.
The beauty of this algorithm is what happens to the bandwidth requirement. In a ring-all-reduce, the amount of data any single GPU has to transmit and receive is completely independent of how many GPUs are in the cluster.
Wait, really? If I have 10 GPUs or 10,000 GPUs, the upload and download strain on a single graphics card is the exact same.
Almost entirely the same. The data is sliced into thinner chunks as you add more GPUs, but the total volume passed by any single node remains constant.
It just scales forever,
It
though.
scales beautifully. Without ring-all-reduce, the entire concept of distributed training would collapse under its own network traffic.
It's just wild to think about. We marvel at the poetry these models can write, but beneath the surface, it's just a highly choreographed ballet of network traffic management.
Traffic management and addition.
Yeah. So, okay, we've established how the machine physically survives the training process. We know parallel layers let the modules read data simultaneously to save network time.
Right.
But that raises a massive conceptual question. What exactly are they reading from? Where is this data living as it moves through the model?
This is the core of it.
This brings us to a concept from the sources that totally shattered my mental image of how an AI works.
You are talking about the residual stream.
Yes.
It is arguably the most important conceptual framework in modern AI interpretability, spearheaded by researchers like Chris Olah. It forces us to completely redefine what a layer actually is.
Because the way I originally learned it, the way most people probably visualize a neural network, is as a strict hierarchy, a destructive assembly line.
A series of transformations.
Right. Let's say you have an image recognition model looking at a picture of a cat. Layer 1 looks at the raw pixels, does some math, and finds all the sharp edges.
Okay.
Then it completely overwrites the original data. It destroys the pixels and passes only the edges to layer 2.
And then layer 2 does its job.
Right. Layer 2 takes those edges, finds shapes like triangles and circles, destroys the edges, and passes the shapes to layer 3. It's totally destructive.
That was the standard paradigm for years, particularly with older convolutional neural networks like AlexNet or VGG. The function was essentially input X goes into the layer and output Y comes out.
And X is gone.
The original X is consumed and replaced by the new representation. It is a sequence of complete destructive transformations.
But the sources make it explicitly clear transformers do not work that way. The residual stream model paints a totally different picture.
It is much more fluid.
Yeah, instead of an assembly line where the product is constantly melted down and reforged, you have to imagine the hidden state of the transformer as a continuous river.
A river of data.
Exactly. A river of data flowing from the very bottom of the model, where your text prompt first enters, flowing straight up to the very top layer where the final answer is predicted.
And the layers are alongside it.
Right. The layers themselves, the attention mechanisms, and the MLPs are not stairs you climb. They are not checkpoints you have to pass through. They are independent factories built along the banks of this shared river.
The river acts as a central, persistent memory bus.
As the river flows past, layer 1 dips a bucket in.
It takes a sample.
It reads the current state of the stream. Inside its factory, it performs its incredibly complex, high-dimensional calculations to figure out what semantic context or grammar is missing.
Okay.
It generates an update, an increment, a delta, and then it pours that bucket of new information back into the river. It writes to the stream.
It adds to it. It doesn't overwrite the water. It just stirs new minerals into the current.
A perfect way to visualize it.
And suddenly, the parallel layers hack we just spent so much time on makes perfect visual sense.
Because in the old sequential way, the attention factory dips its bucket, pours in its new minerals, and then the MLP factory downriver dips its bucket into the newly mixed water.
Right.
But in the parallel hack, the attention factory and the MLP factory are literally standing shoulder to shoulder on the exact same spot on the riverbank.
They are.
They both dip their buckets into the exact same water at the exact same time, do their internal work, and then pour their buckets back into the river together.
Because the fundamental operation of the stream is cumulative addition, the order in which these factories operate becomes highly flexible. You aren't destroying the state, you are just accumulating independent deltas.
And this explains a phenomenon in AI that sounded like absolute science fiction when I first heard it.
Which one?
If you have a fully trained, highly intelligent transformer model, you can open up the code and literally delete entire layers from the middle of the network.
Layer pruning.
Yeah, you can just rip out layer 15 and layer 16, you prune them, and the model still works. It might be slightly less nuanced, but it doesn't crash.
Which breaks the old mental model completely.
Right. If the model was a staircase, taking out a stair means the signal falls into the void. The program errors out.
But under the residual stream paradigm, deleting a layer simply means a factory on the riverbank has been shut down.
Its doors are just closed.
Exactly. It doesn't dip its bucket, and it doesn't add its specific delta to the stream. But the river itself, the river just flows right past the silent factory.
It just keeps going.
The core information containing the original input plus the accumulated additions of layers 1 through 14 arrives at layer 17 perfectly intact. The system is immensely resilient because the stream preserves the foundational data by default.
It's such an elegant way to process information. But to really grasp why this river exists, we have to look at the crisis that birthed it.
We have to rewind the clock to 2015.
Yes, to a legendary architecture called ResNet, residual networks.
ResNet is the tectonic plate upon which almost all modern deep learning rests. Without it, there are no large language models.
Because prior to 2015, the entire field of AI research was crashing headfirst into an invisible ceiling known as the degradation problem.
It was a massive roadblock.
The degradation problem is so completely counterintuitive. You would naturally assume that if a neural network with 20 layers is smart, a network with 50 layers should be a genius.
More layers, more intelligence, right?
Exactly. It has more parameters, more compute, more room to learn complex patterns. But what researchers actually observed was that as they added more layers, the models started performing substantially worse.
And the crucial detail here is that they weren't just failing on new, unseen data, which would be overfitting.
Right, they were failing on the stuff they already knew.
Exactly. They were performing worse on the exact training data they were given. The network itself was somehow rotting from the inside as it got deeper.
It was one of the great paradoxes in machine learning.
From a purely theoretical, mathematical standpoint,
Mhm.
a deeper network should always be able to achieve an error rate at least as low as a shallower network,
Why? I mean, what's the logic there?
because of a concept called identity mapping. Imagine the 20-layer network finds the perfect solution. The 50-layer network should theoretically be able to just copy the exact same weights for its first 20 layers, and then use layers 21 through 50 to do absolutely nothing.
To just pass the data forward perfectly unchanged.
Yes, an identity map. If it did that, it would tie the 20-layer network. But in practice, standard neural networks, trying to learn through sheer brute force, were completely incapable of learning how to do nothing.
The source material provides a fantastic analogy to visualize what the network was trying to do.
The painter analogy.
Yeah. Imagine you are an absolute master painter. I hire you to paint a hyper-realistic, complex landscape. You spend days on it, and it's gorgeous.
Okay.
That represents the successful 20-layer network. Now, I hire a second painter to act as the deeper layers, but I don't let the second painter just walk up to your canvas and add a few details.
Oh, that would be too easy.
Instead, I give the second painter a completely blank canvas. I point to your finished masterpiece and I say, look at that painting. I need you to completely redraw every single tree, every cloud, every blade of grass perfectly from scratch on your blank canvas. And while you're at it, maybe add a bird in the sky.
And that second painter is going to inevitably make mistakes. They will distort the color slightly, they'll misplace a branch, the signal degrades.
And that's what a standard network was doing.
This is what a standard non-residual network was doing. The equation was h of x. Every single layer was trying to learn the entire, complete transformation of the data from scratch.
So as the information passed through dozens of these imperfect force reconstructions, the original data was mutated and lost in the noise.
Enter the ResNet breakthrough. The researchers at Microsoft introduced what might be the most influential, terrifyingly simple equation in AI history. H of x equals f of x plus x.
The plus X is the shortcut. It's the birth of the river.
It fundamentally shifted the mathematical objective of the layer. Instead of demanding that the layer learn the massive, complex mapping of the whole universe, h of x, it provided the original data, x, for free.
So the layer just has to find the difference.
The layer was now only responsible for learning f of x, which is the residual, the difference, the delta.
Going back to the painters, ResNet is me taking your beautiful, finished landscape, physically handing the canvas to the second painter, and saying, do not touch the background is finished. Just paint the bird.
Exactly. The original canvas is the plus x. The bird they paint is the f of x, the tiny increment of new information.
Finding a small perturbation, a tiny adjustment to an already good representation, is orders of magnitude easier for a mathematical model to calculate than reconstructing the entire baseline.
It changes everything.
Okay, but this is where I have to step in and play devil's advocate, because I was thinking about this while reading the sources.
Let's hear it.
If breaking the task into two distinct steps, finding the difference and then adding it back to the original, is so mathematically optimal, why couldn't the AI just figure that out on its own?
It's a fair question.
We use these incredibly powerful optimization algorithms like stochastic gradient descent or ADAM to train these models. Their entire purpose is to find the most efficient mathematical path to the lowest error. Why did human engineers have to manually hardcode this plus X shortcut into the literal architecture?
Why didn't it just learn to be lazy?
Yeah, why couldn't the optimizer just learn that painting the bird was easier than redrawing the canvas?
That is a profound question, and it gets to the very heart of how machine learning actually works. It strips away the anthropomorphism.
We call it artificial intelligence.
But optimizers are fundamentally blind. They are incredibly nearsighted algorithms. They do not have a grand strategy. They operate purely on local gradients.
What does that mean physically for the network?
They feel the mathematical ground immediately beneath their feet and take a single step in whatever direction slopes downward the fastest.
So they can't look at the summit of the mountain and plan a route. They are just wandering down a foggy hill, feeling for the path of least resistance.
Precisely. And in a deep, standard neural network without residual connections, the mathematical landscape they are walking on is treacherous. Trying to ask a traditional neural network layer, which is a massive matrix of weights and biases, to configure itself to perfectly pass data through unchanged is almost impossible.
The identity mapping you mentioned.
Right. It's like trying to balance a bowling ball on a needle. It involves navigating what we call saddle points in high-dimensional space.
A saddle point. literally shaped like a horse saddle. It curves up in one direction but curves down in another.
Yes. If you drop a marble directly into the center of a saddle, it might balance for a microsecond, but any tiny perturbation will send it accelerating off the steep sides.
So it falls out.
It is a highly unstable configuration for the optimizer to find and maintain. But even worse than the saddle points is the vanishing gradient problem.
Let's break that down because I hear vanishing gradient thrown around a lot. But what is the actual math happening there?
During training, the network makes a guess, calculates how wrong it is, which is the error, and sends a signal backward through the layers to adjust the weights. This signal is the gradient,
Right.
but to pass that signal backward through a standard layer, you have to multiply it by the weights of that layer.
Okay, multiplication.
If you initialize a network, the weights are often small fractions, like 0.1. If you have a 50-layer network, you are sending that error signal backward and multiplying it by 0.1 50 times in a row.
Oh, 0.1 times 0.1 is 0.01 times 0.1 is 0.001.
Exactly. By the time you get a few layers back, the number is functionally zero. The error signal just evaporates into nothingness.
The early layers of the network go completely deaf.
They receive a gradient of 0, which tells them everything's perfect, don't change a thing. They stop learning entirely.
That's terrible.
This brings us to a famous 2018 paper that actually visualized these mathematical loss landscapes in 3D. If you plot the error space of a deep standard network, it looks terrifying.
The sources mention this. It looks like a crater, right?
It looks like a jagged, bombed-out crater on the moon. It is a chaotic mess of sheer cliffs, deep ravines, and dead ends. The blind optimizer takes 2 steps and gets permanently trapped in a ditch.
But when you add the ResNet equation, when you hardcode that plus x into the flow,
The landscape transforms. The plus X connection literally irons out the mathematics. It provides an unobstructed, perfectly flat highway for the gradient to flow backward.
so it doesn't get trapped.
The error signal doesn't have to get multiplied by the weights of the layer. It can just skip the layer entirely by traveling backward down the plus X shortcut.
And what does the 3D landscape look like then?
The 3D visualization of residual network's loss landscape isn't a crater. It is a smooth, wide, gentle bowl.
It creates a path of least resistance.
And it creates what we can conceptualize as a mathematical black hole.
A black hole.
When a network is first initialized, the weights are typically random numbers, very close to 0. In a residual layer, if the weights are 0, then the function it calculates, f of x, is 0.
And because the architecture dictates that the output is f of x plus x, if f of x is 0, the output is just x.
Yes. Human engineers didn't teach the AI a clever trick. They completely redesigned the physics of the environment so that the absolute easiest, laziest thing for the nearsighted optimizer to do at the very beginning of training is exactly what we want it to do: preserve the data perfectly.
We use the gravity of mathematics to force the lazy optimizer down the optimal path.
That's the brilliance of ResNet.
That is just amazing. We didn't make the brain smarter. We just paved a perfectly smooth road for it to roll down.
Exactly.
Okay, so we have a deep understanding of how the stream flows. We know why the architecture uses addition to preserve data and keep the optimizers from getting trapped. Now, I want to watch this machine actually think.
Let's do it.
I want to watch this river process human language using a highly specific, relatable example drawn from our sources. Let's trace the evolution of meaning.
The scenario of the riverbank.
Yes. The scenario is this. We input the phrase riverbank. How does the transformer physically, mathematically understand that the word bank in this context refers to a muddy slope next to the water and not a financial institution where you deposit checks?
This is where we transition from purely structural architecture to the dynamic evolution of semantics. We start at layer 0, the absolute beginning of the residual stream.
The source of the river.
Right. The token for the word bank is pulled from the Maltz vocabulary dictionary and dropped into the stream. At this exact microsecond, it exists in a state of chaotic superposition.
Superposition, like quantum mechanics. It's not one thing or the other. It's everything at once.
Precisely. The baseline vector for bank is just a massive list of numbers that represents its statistical usage across all human text.
So it's biased.
Because bank is used more often in financial contexts in the training data, the vector heavily leans toward finance. But it also contains the latent mathematical dimensions for nature, mud, and water. It is a raw dictionary definition containing all possible meanings, entirely devoid of context.
It's just sitting in the water, waiting. Then it flows into the first attention mechanism.
And this is where the famous Q, K, and V query key and value vectors are generated.
To visualize this, the sources suggest thinking of the attention mechanism as a highly mathematical cocktail party where everyone is aggressively networking.
It is a perfect way to visualize the interactions. When the superpositioned word bank enters the attention layer, it undergoes a matrix multiplication that generates its query vector, Q.
Okay, the query.
The query is essentially bank shouting a question across the room to the other words in the sentence.
So bank looks around the party, and its query mathematically translates to, "Hello, I'm the word bank. I am currently having a severe identity crisis. Is there anyone around me who has anything to do with money, interest rates, or conversely, anything to do with nature, water, or geography?"
While bank is broadcasting its query, every other word in the sequence has generated a key vector, K. The key is their name tag.
Okay, so the word river has a name tag.
The word river, which we inputted right before bank, is holding up a key vector. Based on its own dictionary definition, river's key vector mathematically represents: I am a noun deeply associated with nature, flowing water, and ecology.
And here comes the handshake.
The core calculation of the attention mechanism is taking the query vector from bank and performing a mathematical operation called a dot product with the key vector from river.
Let's pause on the dot product because it sounds intimidating. What is it actually doing physically to those numbers?
A vector is just a list of numbers representing coordinates in a high-dimensional space. A dot product takes two of these lists, multiplies the corresponding numbers together, the first number of q times the first number of k, the second times the second, and then adds all those results up into a single final score.
So it just compares them mathematically.
If the numbers in the vectors are pointing in entirely different directions in that semantic space, say a query for finance and a key for Apple, the positive and negative numbers cancel each other out, and the final score is close to zero.
They don't match.
But if the vectors are aligned, if they're pointing in the same direction, like a query looking for nature and a key offering nature, the numbers amplify each other. The resulting score is extremely high.
They match. Bank's query aligns with River's key. The cocktail party networking was a success.
Because that dot product score is so high, Bank is now authorized to extract information from River. This extracted information is the value vector, V.
So V is the actual meat of the interaction?
Yes. The word river takes its core semantic essence water, dirt. Ecology formats it into this value vector and transmits it to Bank.
And this brings us full circle back to the ResNet equation. That value vector extracted from River isn't just floating around, it becomes the f of x. It becomes the residual increment for Bank.
We arrive at the fundamental transformation occurring in the stream, x sub bank plus v sub bank.
So it's adding them.
This isn't just an abstract algebra equation on a chalkboard. It represents a physical geometric movement within the network's brain.
Let's translate that math into physical meaning. What does the x sub bank represent in that addition?
The x sub bank is the anchor. It is the persistent, original identity of the token. It serves as a mathematical tether, saying to the network, no matter how much context we add, do not forget that I am the physical noun bank, and I am located at this specific position in the sentence.
So it keeps it grounded.
If you did not have the original x sub bank anchored in the residual stream, the word's identity would be completely overwhelmed by the context.
It would just become water.
It would dissolve entirely into the concept of water, and the model would lose track of the actual grammar of the sentence.
It's the foundation and the v sub bank.
The v sub bank is the contextual update. It is the modifier. When you add that high-dimensional value vector from river to the anchor vector of bank, you are geometrically shifting bank's coordinates in the semantic space.
So it's literally moving its definition.
The math is literally saying, take the vector for bank, find the dimensions within it that represent finance and suppress them, dilute them. Now find the dimensions that represent dirt, nature, and slopes and mathematically amplify them.
So the stream continues to flow. We now have a heavily modified, wet, muddy version of bank in the river. Then this updated data hits the feed core network, the MLP.
Yes.
What is the MLP doing that attention didn't just do?
If the attention mechanism is about looking outward, looking around the sentence to see what other words are present, the MLP is about looking inward.
Into its own memory.
It looks deep into the model's vast, pre-trained memory banks. The MLP factory dips its bucket and reads this newly updated stream. It sees a vector that represents a bizarre, highly specific blend of bank and water.
And that triggers something.
This specific coordinate in the high-dimensional space acts as a trigger. It activates a specific pathway in the MLP's massive matrix of weights. The model effectively realizes, I have seen this combination billions of times in my training data. River plus bank equals riverbank.
It accesses its internal encyclopedia.
It synthesizes all the geographic, ecological, and spatial data it has memorized about riverbanks over its training, formats that profound knowledge into another delta, and writes it back into the stream.
Wow.
By the time this specific token reaches the final output layer of the transformer, the financial superposition it started with has been entirely washed away. The vector now perfectly, unambiguously represents a muddy shore.
It's breathtaking how elegant that is. It builds complex human context incrementally, layer by layer, factory by factory, simply by adding lists of numbers together.
It is incredibly elegant.
But exploring this raised a really interesting counter scenario in my head. If the entire magic of the attention mechanism relies on looking at other words to extract value vectors, what happens when a word is entirely alone?
An isolated word.
Right. What if the user prompt is just the isolated word bank followed by a period? There is no river, there is no sentence, there is no external context to draw from.
Okay.
My intuition says, if there is no context, the dot product score with everything else is 0. Therefore, the value increment, the v, should just be 0. The model shouldn't add anything. Why not just use the perfect original X vector? Why mess with it if there's nothing to add?
It is a deeply logical intuition,
Mm-hmm.
but it assumes a premise that is fundamentally false.
Ooh.
It assumes that the original X vector at layer 0, the dictionary lookup, is perfect. What the deep dive into the architecture reveals is that the initial embedding is far from perfect. It is, in fact, a raw, unrefined OR.
Raw or? What do you mean by that? It's the dictionary definition. Shouldn't it be the purest representation of the word?
It is pure, but it is entirely unformatted for the complex mechanics of the upper network. The layer 0 embedding is an anti-causal lookup table.
Meaning what, exactly?
When the word bank is blindly pulled from the matrix at the very beginning, that vector has no idea what is happening. It doesn't know what position it holds in the sequence. It doesn't know what the final task of the model is. Is it translating, summarizing, or predicting? It is a blunt, static instrument.
So it's just a raw ingredient.
The final classification layer of the model, the highly sophisticated part at the very top that actually predicts the next word, cannot read this raw OR. The top layer only speaks the highly refined, complex, high-dimensional language that is produced by passing through multiple transformer blocks.
Okay, so if it's raw or, and there are no other words around to help refine it, how does it get processed?
Through a mechanism called self-attention.
Self-attention.
Literally, the token directing its attention mechanism entirely upon itself. In the case of an isolated word, or even just in the very early layers of a complex sentence where the model is still doing basic formatting, a token will look at itself. The query vector generated by bank will be mathematically compared to the key vector generated by bank.
And naturally, they are a perfect match.
The dot product score on its own diagonal in the matrix will be massive.
Right. Because of that perfect match, bank authorizes the extraction of a value vector from itself.
And this v vector is absolutely crucial. It is never 0. Adding 1 times v sub bank to x sub bank is the model's way of formatting its own data.
It's smelting the ore.
It's taking the raw OR of the embedding and smelting it. It is restructuring its own semantic features into the complex, high-dimensional format that the subsequent layers expect to receive. It is an internal, necessary upgrade just to make the data compatible with the rest of the brain.
That makes perfect sense from a data pipeline perspective. The input has to match the expected format of the functions downstream. But the sources also highlight a secondary, highly rigid constraint here that forces this behavior, and it comes back to the physical hardware.
The GPU constraints.
Why can't the model just be smart enough to write an exception? Why can't it say, okay, I'm looking at myself, so I'll generate a V of 0, but if I'm looking at river, I'll generate a real V?
Because of the relentless, unforgiving nature of GPU matrix multiplication. To achieve the blinding speeds required to run these models, GPUs perform single instruction, multiple data operations.
CMD?
CMD. They execute the exact same mathematical instruction across thousands of data points simultaneously.
Yeah.
We have to view the value matrix, V, not as a series of individual calculations, but as a public shared photo album that is calculated and published simultaneously for the entire sequence in one massive mathematical strike.
And you can't put if-then conditional statements inside a dense matrix multiplication.
You cannot. Branching logic, if this, do that, else do this, destroys the parallelism of the GPU. The GPU wants to multiply massive grids of numbers uniformly.
So it has to be the same rule for everyone.
If the word bank somehow produced a 0v vector to save itself from being updated, it would be publishing a blank page to the shared public album.
Oh, I see.
That means any other word in the sequence that might be genuinely looking for the concept of bank would query the album, find the blank page, and get absolutely nothing. The entire contextual web would collapse.
Therefore, the system is mathematically locked.
V must always contain the fully realized, refined, semantic features of the word, whether it is passing those features to a neighboring word or passing them back to itself to smelt its own ore.
It's a fascinating reality check. We talk about AI as this ethereal, infinitely flexible intelligence, but at the absolute bottom level, its thoughts are strictly dictated by how silicon chips handle dense grids of numbers.
It all comes back to the hardware.
All right, we've given the word its meaning, we've smelted its raw ore, we've given it the ability to absorb context from its neighbors. But if you step back, there is a massive, glaring hole in this architecture.
What's the whole?
How does the stream know the order of the words?
Sequence.
Yeah. If I put in the sentence, the dog bit the man, and then I put in the man bit the dog, the set of words is identical.
The exact same tokens.
The cocktail party has the exact same attendees. The queries and keys will all find the exact same matches. Without some understanding of sequence, a transformer is just a bag of words. It is completely blind to grammar.
This was the Achilles heel of early attention mechanisms. The mathematical operations of attention are inherently permutation invariant. They do not care about the order of the inputs.
So how did they fix it?
To give the model a sense of time, a sense of sequence, engineers had to invent position embeddings.
When I was first trying to wrap my head around this in the sources, I had a hypothesis. Since the query and key matrices are already doing this incredibly complex matching game, could they just be trained to produce and recognize index numbers?
Like a timestamp.
Right. Like, could the query vector for the word bank be trained to say, I am looking for the word that exists at index position 2. And the key vector for river says, hello, my name tag says I am at index position 2. Could they just match based on absolute sequence numbers?
Your hypothesis tracks perfectly with the historical development of the technology. That is exactly what early position embeddings attempted to do.
Sure, they did try that.
They tried to hard-code absolute index markers into the vectors, position 0, position 1, position 2. But absolute positioning fails catastrophically when you try to scale the model's context window.
Why does it fail? If it knows how to count, shouldn't it just keep counting?
Because neural networks don't count the way a classical program does. They learn statistical patterns based on the data they see during training.
Okay, so it learns a pattern, not a number.
If you train a model on sequences that are strictly 1,000 words long, it learns the specific high-dimensional mathematical signature of position 999. It understands what that absolute coordinate feels like.
Right.
But if you release that model into the real world and ask it to read a 5,000-word essay, it encounters position 4,000. It has never seen the mathematical signature for 4,000 in its entire existence.
Because it only ever went to 1,000.
It is completely out of its training distribution. The model panics, hallucinates, and the logic breaks down entirely.
Because absolute coordinates don't generalize. Which leads us to the modern solution, the standard used in cutting-edge models like Lemma and DeepSeek, ROPE, rotary position embedding.
Rotary implies spinning.
Does it actually physically rotate the data?
It rotates the data vectors, but in a complex, multidimensional geometric space.
Hard to visualize.
Instead of adding a static absolute number to the word, ROPE applies a mathematical rotation to the query and key vectors right before they do their handshake. Imagine every word's vector is a hand on a clock face.
Okay, I'm picturing the clock.
The rotation is dictated by the word's position in the sequence. Token 1 is rotated by a specific baseline angle. Let's call it theta, so it spins forward slightly.
Okay, 1 tick on the clock.
Token 2 is rotated by 2 theta. Token 5 is rotated by 5 theta.
So the further down the sentence you go, the further around the clock face your vector gets spun. The sheer position in the sequence dictates the physical angle of the data in the mathematical space.
Precisely. Now, recall how the attention mechanism decides if two words are a match.
It uses the dot product.
The profound, almost magical property of performing a dot product on two vectors that have been rotated in this manner is that the underlying trigonometry automatically extracts the angle difference between them.
Wait, let me make sure I understand the math. If token 5's query vector, which has been rotated by 5 theta, performs a dot product with token 1's key vector, which was only rotated by 1 theta.
The mathematical result of that handshake is inherently tied to the relative difference, 4 theta.
It just subtracts the angles.
The model is no longer memorizing absolute static positions like I am at position 5. It naturally geometrically understands relative distance. The math simply tells it the word you are looking at is exactly 4 steps away from you.
Oh, that is staggeringly elegant.
It truly is.
Because if it only cares about relative distance, it doesn't matter if it's looking at the gap between word 1 and word 5 or the gap between word 99,000 and 99,004. A distance of 4 steps is a distance of 4 steps. The angle difference is identical.
And that is exactly how modern models achieve massive context windows. They can extrapolate to read entire books because they aren't afraid of high absolute numbers anymore. They have a universal geometric understanding of distance and grammar.
We've laid out the perfect machine. We've seen the hardware hacks of parallel layers. We've traced the flow of the residual river.
We've covered a lot of ground.
We watched words absorb meaning through self-attention, and we've seen them learn the rules of grammar by spinning around a multi-dimensional clock face.
But there's a missing piece.
Yeah, as perfectly engineered as this all is, here is the part that still feels like actual magic to me. How does it get built?
The training process.
I understand how it works once it's finished, but how does it learn this incredible geometry from absolutely nothing? Let's picture the exact moment a model is born, the big bang of initialization.
Okay, day 0.
I am an engineer. I sit at my terminal, I write model equals llama, and I hit enter. What actually exists in the memory banks in that first microsecond?
Chaos. Pure, meaningless, static noise.
Just random numbers.
The embedding matrix, which acts as the dictionary, the dense attention matrices, the massive feed-forward network weights, they are all initialized with tiny pseudo-random fractions.
So it's a completely blank slate.
At that exact microsecond, the vector for the word bank and the vector for the word hospital are functionally identical. They're just random coordinates. The network possesses zero intelligence. It knows nothing of language, nothing of grammar, nothing of humanity.
So how does it cross the chasm from random noise to understanding quantum physics? Walk me through the exact timing of the update. I want to understand the physical moment the AI gets smarter.
The evolution from noise to intelligence happens through a relentless, iterative cycle consisting of 3 distinct phases: the forward pass, the backward pass, and the optimizer step.
Let's look at the forward pass first.
The engineers feed a massive batch of human text, say, a chunk of Wikipedia, into the model. The model takes its random numbers and dutifully performs all the complex math we just discussed.
It spins the clock faces, it mixes the rivers.
It rotates the vectors, it calculates the dot products, it pours deltas into the residual stream, and at the very end, it makes a guess about what the next word should be.
And because every single gear in its head is made of random numbers, its guess is going to be hilariously, spectacularly wrong. It will output complete garbage.
It will be entirely incorrect. But here's the critical mechanical detail. During this forward pass, all the parameters, all the billions of weights, are strictly read-only.
Oh, so nothing changes yet.
The model is observing the data, and the data is flowing through the architecture, but no permanent changes are being made. The memory banks remain entirely static.
Okay, so it makes a terrible guess. The forward pass ends, then comes the backward pass.
The model calculates its loss. It mathematically quantifies exactly how spectacularly wrong its prediction was compared to the actual text from Wikipedia.
And then it sends that error signal back.
Then the system calculates the gradients. This is the application of calculus, specifically the chain rule. The error signal flows backward from the top output layer, down through the MLPs, down through the attention mechanisms, all the way to the foundational embedding matrix at the bottom.
It traces its steps.
A math calculates the exact derivative, the exact responsibility that every single random weight had in contributing to the massive error.
So this is when the AI learns. This is when the weights change.
No. Surprisingly, still no weights change.
Wait, really? Even on the backward pass?
During the backward pass, the network is merely accumulating demerits in a separate temporary memory buffer. It is calculating the theoretical adjustments.
It's just making a list.
It's essentially saying, if I were allowed to change, I would move this specific weight up by 0.001, and I would move this other weight down by 0.005 to reduce the error. But it does not touch the core memory.
It's just taking notes on what it should do. It's planning. So when does the actual learning occur?
The strike of the optimizer. In programming frameworks like PyTorch, this is a single specific command. Optimizer.step.
The optimizer step.
In one singular unified instant at the very end of the batch, the optimizer gathers all those millions of accumulated demerits from the temporary buffer, and it updates the embedding matrix and all the internal layers simultaneously.
Boom. In 1 microsecond, the entire network shifts.
Yes.
The random numbers become just a tiny microscopic bit less random. They are nudged collectively toward meaning.
Exactly. And it's crucial to understand that the foundational dictionary, the embedding layer, is updated with the rest of the network. The dictionary itself learns dynamically.
This was not always the standard practice in machine learning, was it?
No, it wasn't.
Right. The sources spent a lot of time contrasting modern end-to-end training with the older methods of using pre-trained embeddings. What was the old way?
In the older generation of models, engineers would use pre-trained dictionaries, like Word2Vec. They would train the vocabulary matrix separately on a massive data set, plug that finished dictionary into their new neural network, and then freeze it.
Freeze the dictionary.
During the optimizer step, the upper layers of the network would update and learn, but the foundational dictionary remained locked and static.
The text uses a really evocative analogy for this. It compares freezing the embedding layer to trying to dance on a rigid rock.
A very apt metaphor.
If the foundation, the vocabulary, is frozen and cannot adapt to the specific nuances of the task the model is trying to learn, the upper layers of the network have to contort themselves into incredibly awkward, inefficient mathematical shapes just to compensate for the rigid foundation.
It severely limits the ultimate potential of the model.
To solve that, the field moved toward fine-tuning, or domain adaptation. You still start with the pre-trained Word2Vec dictionary to give the model a head start, but you unfreeze the foundation. You allow the optimizer to update the dictionary alongside the rest of the network.
And this is where we see the geometry of meaning actually physically move.
Right. If you take a general model and fine-tune it by exclusively feeding it geology textbooks, the dictionary adapts. Initially, the vector for bank might sit squarely between the cluster of finance words and the cluster of nature words.
But as the optimizer step happens over and over,
Yeah, as the gradients constantly punish the model for guessing finance words in a geology context, the weights slowly, physically pull the coordinates of the word bank away from Wall Street and drag it deep into the semantic cluster of rivers, sediment, and earth.
the dictionary molds to the domain.
Which brings us to the ultimate question of modern architecture. If starting with pre-trained weights provides such a massive head start, why do the most powerful models today, Llama, GPT-4, Claude, start from pure, absolute random noise? Why throw away the head start and build from scratch?
Yeah, if the whole goal is to save compute time and optimize, why start with amnesia?
It seems backwards.
There are two forces driving this, one mechanical and one philosophical.
Let's hear the mechanical one first.
The mechanical reason is the evolution of tokenizers. Older models had relatively small vocabularies. Modern models use massive, multilingual tokenizers that break words down into highly optimized subword fragments.
Oh, they don't even use whole words anymore.
Because the size and structure of the vocabulary matrix fundamentally changed, you literally cannot mathematically plug the old Word2Vec dictionary into the new architecture. The puzzle pieces don't fit.
But even if they could make them fit, the sources suggest they still wouldn't use them. Why?
The sheer, incomprehensible volume of the data.
The scale of it all.
We are no longer training models on a few gigabytes of text. We're talking about training runs that consume 15 to 30 trillion tokens.
Trillion.
When you have a data set that encompasses essentially the entirety of recorded human text, code, and mathematics, the force of the gradient whip is absolute.
The gradient width.
The optimizer forces the random noise to evolve into a perfect custom-fit semantic geometry far faster and with much greater purity than if the model had to inherit an older model's biases and structural baggage.
So the scale of the data is so massive, it completely washes away the need for a head start. The blank slate actually becomes the ultimate advantage because it allows the model to build a foundation perfectly optimized for its exact massive scale.
Precisely.
Okay. Let's take a deep breath and look at the whole picture we've painted today.
We've gone from the hardware to the philosophy.
We started in the physical realm, looking at how engineers cheat the laws of hardware latency. They force layers to read data in parallel, accepting a tiny mathematical blind spot just to have the communication times across thousands of GPUs using ring-all-reduce.
A necessary sacrifice.
We saw how they solved the degradation of deep networks by smoothing out the mathematical craters with the ResNet equation, giving birth to the residual stream, a continuous river of information where independent factories just add their small increments of knowledge.
The F of X plus X.
We watched the raw ore of random noise self-organize into semantic intelligence. We saw words format themselves through self-attention, extract meaning from their neighbors through dot product handshakes, and learn the strict rules of human grammar by rotating through dimensional space on a clock face.
It is a breathtaking triumph of complexity.
Very amazing.
The intelligence you see on the screen does not arise from a complex, hard-coded brain. It arises from incredibly simple, highly repetitive mathematical rules applied iteratively over trillions of cycles.
And this is why you want to do this deep dive. Why does knowing the mechanics of all reduce a rope matter to you?
It matters deeply.
It matters because it fundamentally changes your relationship with the tool. When you sit down today and you type a prompt into an AI, you aren't just querying a database. You aren't doing a fancy Google search.
Not at all.
You are dropping a stone into a meticulously engineered residual river. You are watching ripples of multidimensional math extract context, rotate through geometric space, and synthesize a coherent thought from what was, fundamentally, a silicon void. You are interacting with a dynamic, physical representation of human knowledge.
Stripping away the illusion of magic doesn't diminish the achievement, it elevates it. When you understand the architecture, you realize that artificial intelligence is simply the optimal path of least resistance, discovered by a blind optimizer wandering across a landscape of trillions of parameters.
And that leads me to a final thought for you to take away from this.
The philosophical seed.
We designed this architecture, the residual stream, the f of x plus x equation. We built it to solve a purely mathematical problem. We just wanted to stop gradients from vanishing in deep networks so we could make them bigger. It was an engineering hack.
Just a way to optimize.
But in doing so, we mathematically forced the AI to build its reality incrementally. We forced it to maintain a persistent, anchored core identity, the X, while simultaneously constantly updating that identity with new contextual deltas from its environment, the F of X.
A continuous, unbreakable integration of past foundations and present context.
Does that sound familiar?
It really does.
Because the more you look at it, it makes you wonder, isn't that exactly how human memory and consciousness operate?
We certainly aren't static databases.
We aren't static databases either. We don't overwrite our brains every time we see something new. We are a residual stream of our past, constantly updated and modified by the attention we pay to the present moment. Every new experience, every new conversation is just a value vector added to our anchor.
We just accumulate deltas.
At the beginning of this deep dive, we said an AI is a black box. But maybe, by prying the black box open, we didn't just find a bunch of clever math. Maybe we accidentally engineered a mirror. Think about that the next time you change your mind.